Hello guys and girls, in this video I will tell you about geology as a science. Geology is a branch of earth science concerned with both the liquid and solid earth, the rocks of which it is composed and the processes by which they change over time. Geology can also include the study of the solid features of any terrestrial planet or nature satellite such as Mars or the Moon. Modern geology significantly overlaps all other earth sciences, including hydrology and the atmospheric sciences, and so is treated as one major aspect of integrated earth system science and planetary science. Geology describes the structure of the Earth on and beneath its surface and the processes that have shaped the structure. It also provides tools to determine the relative and absolute age of rocks found in a given location and also to describe the histories of those rocks. By combining those tools, geologists are able to chronicle the geological history of the Earth as a whole and also to demonstrate the age of the Earth. Geology provides the primary evidence for plate tectonics, the evolutionary history of life, and the Earth's past climates. Geologists use a wide variety of methods to understand the Earth's structure and evolution, including field work, rocks description, geophysical techniques, chemical analysis, physical experiments, and numerical modeling. In practical terms, geology is important for mineral and hydrocarbon exploration and exploitation, evaluating water resources, researchers' understanding of nature hazard, the remediation of environment problems, and providing insights into past climate change. Geology is a major academic discipline and it is central to geological engineering and plays an important role in geocli- geocli- geotechnical engineering. Geological materials. The majority of geological data comes from research on solid earth materials, meteorites, and other extraterrestrial nature materials are also studied by geological methods. Minerals. Minerals are nature occurring elements and compounds with a definite homogeneous chemical composition and ordered atomic composition. Each mineral has distinct physical properties and there are many tests to determine each of them. The specimens can be tested for luster, color, stick, hardest, breakage pattern, specific gravity, effervescence, magnetism, taste. Rocks. A rock is any nature occurring solid mass or aggregate of minerals or mineraloids. Most research in geology is associated with the study of rocks as they provide the primary record of the majority of the geological history of the Earth. There are the three major types of rocks: igneous, sedimentary, and metamorphic. The rock cycle illustrates the relationship relationships among them. See diagram. When a rock solidifies or crystallizes from melt, magma, or lava, it is an igneous rock. This rock can be weathered and eroded, then redeposited and light-fed into a sedimentary rock. It can then be turned into a metamorphic rock by heat and pressure that change its mineral content, resulting in a characteristic fabric. All three types may melt again, and when this happens, new magma is formed from which an igneous rock may once more solidify. Organic matter such as coal, bitumen, oil, and natural gas is linked mainly to organic-rich sedimentary rocks. To study all three types of rock, geologists evaluate the minerals of which they are composed and their other physical properties such as texture and fabric. Unlightified material. Geologists also study unlightified materials that lie about the bedrock. This study is often known as Quaternary geology. After the Quaternary period of geology history, which is the most recent period of geologic time. Magma is the original unliquefied source of all igneous rocks. The active flow of molten rock is closely studied in volcanology, and igneous petrology aims to determine the history of igneous rocks from their original molten source to their final aura crystallization. Whole ear structure. In the 1916s, it was discovered that the Earth's lithosphere, which includes the crust and rigid uppermost portion of the upper mantle, is separated into tectonic plates that move across the plastically deforming solid upper mantle, which is called the astronosphere. This theory is supported by several types of observations, including sulfur spreading and the global distribution of mountain terrain and seismicity. There is an intimacy coping between the movement of the plates on the surface and the convection of the mantle. Thus, oceanic plates and the adjoining mantle convection currents always move in the same direction because the oceanic lithosphere is actually the rigid upper thermal boundary layer of the convecting mantle. This coping between rigid plate moving on the surface of the Earth and the convection mantle is called plate tectonics. The development of plate tectonics has provided a physical basis for many observations of the solid Earth. Long linear regions of geological features are explained as plate boundaries. For example, mid-ocean ridges, high regions on the seafloor where hydrothermal vents and volcanoes exist are seen as divergent boundaries where two plates move apart. Arcs of volcanoes and earthquakes are theorized as convergent boundaries where one plate subducts or moves under the another. Transform boundaries such as the San Andreas fault system resulted in widespread powerful earthquakes. Plate tectonics also has provided a mechanism for Alfred Wegener's theory of continental drift, in which the continents move across the surface of the Earth over geological time. They also provided a driving force for crystal deformation and a new setting for the observation of structural geology. The power of the theory of plate tectonics lies in its ability to combine all of those observations into a single theory of how the lithosphere moves over the convection mantle. ER structure. Advanced in seismology, computer modeling, and mineralogy and crystallography at high temperatures and pressures give insight into the internal composition and structure of the Earth. Seismologists can use the arrival times of seismic waves to image the interior of the Earth. Early advances in this field showed the existence of a liquid outer core and a dense solid inner core. Those advances led to the development of a layered model of the Earth, with a crust and lithosphere on top, the mantle below and the outer core and the inner core below that. More recently, seismologists have been able to create detailed images of wave speeds inside the Earth in the same way a doctor images a body in a CT scan. Those images have led to a much more detailed view of the interior of the Earth and have replaced the simplified layered model with a much more dynamic model. Mineralogists have been able to use the pressure and temperature data from the seismic and modeling studies alongside knowledge of the elemental composition of the Earth to reproduce those conditions in experimental settings and measure changes in crystal structure. Those studies explain the chemical changes associated with the major seismic discontinuities in the mantle and show the crystallographic structures expected in the inner core of the Earth. Geological time. The geological time scale encompasses the history of the Earth. It is demarcated at the earliest by the days of the first solar system material, which is beginning of the informally recognized Dim Eon, a division of geological time. At the later end of the scale, it is marked by the present day. Time scale of the Earth. The following 5 timelines show the geologic time scale to scale. The first shows the entire time from the formation of the Earth to the present, but this gives little space for the most recent eon. The second timeline shows an expanded view of the most recent eon. In a similar way, the most recent era is expanded in the third timeline, the most recent period is expanded in the fourth timeline, and the most recent epoch is expanded in the fifth timeline. Dating methods. Relative dating. Methods for relative dating were developed when geology first emerged as a natural science. Geologists still use the following principles today as a means to provide information about geological history and the timing of geological events. The principle of uniformitarianism states that the geological processes observed in operation that modify the Earth's crust at present have worked in much the same way over geological time. A fundamental principle of geology advanced by the 18th century Scottish physician and geologist James Hutton is that the present is the key to the past. In Hutton's words, the past history of our globe must be explained by what can be seen to be happening now. The principle of intrusive relationship concerns cross-cutting intrusions. In geology, when an ingenious intrusion cuts across a formation of sedimentary rock, it can be determined that the igneous intrusion is younger than the sedimentary rock. Different types of intrusions include strokes, lacolites, batolites, sills, and dikes. The principle of cross-cutting relationships pertains to the formation of faults and the age of the sequences throughout which they cut. Faults are younger than the rock they cut. Accordingly, if a fault is found that penetrates some formations but not those on top of it, then the formations that were cut are older than the fault, and the ones that are not cut must be younger than the fault. Finding the K-bet in those situations may help determine whether the fault is a normal fault or a thrust fault. The principle of inclusions and components states that with the sedimentary rocks, if inclusions are found in a formation, then the inclusions must be older than the formation that contains them. For example, in sedimentary rocks, it is common for gravel from an older formation to be repied up and included in a newer layer. A similar situation with igneous rocks occurs when xenolites are found. Those foreign bodies are picked up as magma or lava flow and are incorporated later to cool in the matrix. As a result, xenolites are older than the rock that contains them. The principle of original horizontality states that the deposition of sediments occurs as essentially horizontal beds. Observation of modern marine and non-marine sediments in a wide variety of environments supports this generalization. This generalization. The principle of superposition states that a sedimentary rock layer in a techno- tectonically undisturbed sequence is younger than the one beneath it and older than the one above it. Logically, a younger layer cannot slip beneath a layer previously deposited. This principle allows sedimentary layers to be viewed as a form of the vertical timeline, a partial or complete record of the time elapsed from deposition of the lowest layer to deposition of the highest bed. The principle of faunal succession is based on the appearance of fossils in sedimentary rocks. As organisms exist during the same period throughout the world, their presence or absence provides a relative age of the formations where they appear. Based on principles that William Smith laid out almost 100 years before the publication of Charles Darwin's theory of evolution, the principles of succession developed independently of evolutionary thought. The principle becomes quite complex, however, given the uncertainties of fossilization, localization of fossil types due to literal changes in habitat, and that not all fossils formed globally at the same time. That is all. Thank you for watching.